Seriously. All right. Let's see here. So we are ready to ask the question if a tree is balanced or not balanced. Does that sound right? Did we actually ask that yet? So we visited level order. We were talking about tree rotation. We started introducing keyboard, nice. We started introducing the AVL trees and the left-left, left-right, right-right, right-left, out of balance thingy-majiggy. Okay, so now we need to be able to ask the question, am I out of balance? And we decided that out of balance means that from a full tree perspective, the left side of the tree is more than 1 in depth away from the right side of the tree. All right, so we need to be able to ask our tree in general, are you out of balance? In order for him to do that, he needs to get the depth of the left tree and get the depth of the right tree. So a binary search tree needs to be able to answer what is its depth. All right, so and this is where we were talking about the max numbers here. Because as I'm going down this tree, so for instance, if we ask this top tree what its depth is, okay, we probably wouldn't do that because we're more interested in the left and the right. But if we did ask the top tree what its depth is, so we can see the example here, its depth is going to be the max of the depth of the left and the depth of the right. Okay, it's going to be the max of that, and it's going to be 1 plus the max of that is going to be his depth. All right, so the max of the left tree here is 2, right? 1, 2. The max of the right tree is 3. So this guy's depth would be 4, assuming we started with a 1, right? All right, so we need to be able to determine the depth of a tree given a root node. All right, so we need to ask that question. Depth of tree algorithm. All right, so we start here. So the depth of any tree given its starting node, we currently have our binary tree set up as a tree of trees. So we kind of have it set up the right way, if you will. So to ask a binary search tree what its depth is, it's going to be 1 plus the max of its left and right child depth. Okay. Well, what am I doing here? Same app, different slide. All right, so if we are at, so start with a binary search tree. Depth is equal to 1 plus max of depth of left, comma, depth of right. Okay, so what is depth of left? What is depth of right? We circle back up. So this guy is depth of BST. That's what this algorithm is. So left is a BST. Right is a BST. So we're just going to keep looping back up here, right? Now, we do need to have some caveats. If left is null, return a depth of 0. If right is null, return a depth of 0. Okay, so this is a recursive algorithm, or recursive-ish algorithm, right? Since it's tactically a different binary search tree we're talking to, but same function. All right, so we need to teach our binary search tree how to return its depth. And its depth will always be 1 for itself, plus the maximum of the depth of left and the depth of right, with the caveat that if left or right is null, the default depth will be 0. That'll make the math not crash the app. Okay, so let's go and write this. This is going to be inside of binary search tree, and we'll put it right up here at the top. So we're going to call this guy. Actually, let's make this private, because we might not necessarily be interested in the depth external to our binary search tree, but we do need to have access to this function from every binary search tree. And since every single thing we're dealing with here is a binary search tree, is a BST, we would have access to private members of that BST, right? Okay, so public, private, protected. Public means we have access to it everywhere. Private means we have access to it anywhere inside of a class called BST. Even if it's different instances of that class, we would still have access to private members. All right, so this is going to be private int depth. This guy would take in no parameters. Okay, and we could really do this as a one-liner probably. That might actually be an interesting line to write just to see it. So we're going to return 1 plus. Now we want the max depth of the left. So we're going to ask, have we talked about inline if statements in here at all? At any point in time? I'll show them to you. It's not something I promote very often, but it's kind of interesting. So the syntax for an inline if statement is Boolean expression followed by a colon, actually no, followed by a question mark, followed by a true statement, followed by a colon, followed by false statement. And it will boil down to those two values, which of those two values it is. All right, so we'll see this as an example here. So we're going to return 1 plus, and we want the max depth of left or right. So we're going to say max dot max, and this is going to take in two integers. Have I showed you math.max before? All right, well, we can certainly write an if statement that says if this number is greater than this number, return this one. Else return something else. Math.max automates that. Just writes that if statement for us. It's not doing anything earth-shattering. It's just a nice little convenient way that's built into Java. And just as a quick example here, if you just do math dot, you'll see there's a whole bunch of stuff in here for absolute value and min and rounding, all sorts of mathy stuff. Okay, so we're going to say math.max, and we're going to want the version that takes in two integers. Okay, and the first number is either going to be 0 or the depth of left, right? Not left. All right, so we're going to use an inline if statement here. So I'm going to put this in parentheses. I think it should allow us to do an inline if statement in here. So we're going to say math.max. So the question we're going to ask here is, we need to ask roots left. So this dot root dot get left tree is equal to null. That's a true statement. If the left tree is equal to null, we want to boil down to 0. Else, we want to boil down to this dot root dot get left tree dot get, or just what, dot depth, like that. So that is first part of this, comma, and I'm going to kick it down a line here. That's the second part. That's that. And what is this guy complaining about? Not resolve method depth, D-E-P-T-H. Huh?
It's on a binary
Oh, root is a binary tree. Why is that? So really we need to call root depth. So a binary search tree is our wrapper class that's filled with binary trees, right? So this is the way we access it, but we have a binary tree of binary trees. So this guy's going to have a left and right that's a binary tree. Okay, got it. So we're going to move this depth. Just copy that real quick. And now we're going to say return 1 plus root. Actually, we want to be return 1 plus. It's just going to be root dot depth, and we'll go write that here. So that's our depth function inside of binary, or inside of BST. Then we're going to write the same thing inside of binary tree, and this guy is going to just return left tree is equal to and this guy will return right tree. Right tree. Okay. Okay, and that guy can no longer be private because BST and binary tree are not the same class. So this needs to be public because they're also not inheriting from each other. All right, so when we ask a binary search tree in general what its depth is, which we may not actually do, we might, we might just ask it if it's out of balance. So we actually might do this. Boolean. Well, for right now, let's just ask if get the depth of the tree. Since we know the depth of our current tree, so we'll be able to test it since we've hard-coded a tree. All right, so we'll get the depth, which we'll ask our root node, which is a binary tree, to return its depth. What does this guy do? He returns 1 plus the maximum value of, here's our first inline if statement. So first inline if statement asks the question, if the left tree is null, boil down to 0. Otherwise, boil down to the depth of my left tree. Does that make sense? So that's what an inline if statement allows us to do. It allows us to toggle between two possible values without writing a big if statement that says, if this is true, add 0. Else, add the depth of this value. Okay? So it's kind of a space saver, if you will, and works out well in these types of situations where it's one number or another number. If you need to do more than one thing inside the body of an if statement, you would not use an inline if. So if the left tree does not exist, boil down to 0. Otherwise, grab its depth and pass it as the first parameter to max. If the right tree does not exist, boil down to 0. Otherwise, boil down to its depth and pass it as the second parameter max. Math.max will then boil down to a single number, which is the maximum of those two values, which will add to 1 and return for the depth of this particular binary tree. Keeping in mind that when we call depth on the left tree and depth on the right tree, we're pseudo-recursively calling this same function. A different binary tree's version of that depth function, but still calling that same function. And that guy might then make pseudo-recursive calls down the line. Make some sense? All right, so this is depth. Now let's quickly open up our AVL tree. Ooh. Because this guy shows us our trees over here. Oh wait, no. Our trees that we're currently building are just tree traversal. are these trees. All right, so even though these are balanced trees right now, the depth of this should be 1, 2, 3, 4. If it works, that's what we should get out of it. All right, so let's go back to our studio. We'll do this inside of main activity. Here's all our visit and order stuff. We'll just comment that out for the moment. And we'll go ahead and do system.out.println tree, dot, oh, I made that private too, didn't I? Tree.depth. Okay. Let's just do depth is equal to that so we can kind of see it. All right, so let's run this guy, and we expect to get a 4 out of this. Yeah, I'm not even going to need lunch today as much of this. See, I usually use opaque cups, that way I don't fall victim. It's all a mystery. All right. Why did we get the depth twice? There's depth. Calls this depth, which just returns it, which calls this depth. Why did that happen twice? Let's run it one more time and see if it was just a weird launch thing where onCreate got called twice in our main activity. All right, yeah, it's just running once there. Yeah, maybe it was just when it first launches, it doesn't make a whole lot of sense actually, but I guess whatever. All right, so we got a depth of 4 there. So let's go ahead and let's try to knock it off balance. So we'll add a couple of values that should go to the right side. So if I put in a Z there, that should now add that to the left side of the, or I'm sorry, the right side of the tree, larger. So now we should get a depth of 5. Oh, we got a depth of 4 again. Oh, does it not fill out? Hold on, let's look at our, yeah, it would have gone right here. So still 4, so we need to do 2 Z's. So now we should get a depth of 5. All right, and let's see, we'll just do another Z. That should give us a depth of 6. So now we know how it's out of balance. It's slow because it's probably still trying to launch that angular form from last night. I'm going to look at that today because that's just frustrating me. Why it doesn't launch a form that you just put inside the script? Something stupid. I hate Angular. Plus, we're getting to the point now we have to use template engines, I think, because our HTML is getting a little crazy in there. Yeah, this is from the grad class. We're building a Uber for snow removal type thing, and this button right here is supposed to launch like a checkout with credit card thing, and it doesn't launch it if we have it here. If we move it outside of this form, it works just fine. But that's kind of stupid stuff. So you think Android's bad. Android's way better than Angular. It's just garbage. All right. So now we're clearly going to be out of balance, right? So depth seems to be working. So now let's update BST to no longer return depth, but to return a Boolean. Is out of balance. And we're going to, well, we're going to have to return this dot root dot is out of balance, which is just kind of the nature of a tree of tree things since we had to build that wrapper. So now we're going to have to write this function inside of our binary tree. All right, and then from a binary tree perspective, is out of balance is going to be if the depth of left and the depth of right are more than 1 apart. So the absolute value of depth of left minus the depth of right is greater than 1. So let's see. We're going to need to do another inline if statement. So we're going to say math dot, let's break it down into a couple of lines here at least. So we're going to say int left depth is equal to this dot left tree equal to null question mark 0 colon. And by the way, this syntax is from C. So this goes back to that whole evolution of our languages. This inline if statement thing came from a really old language. So if you ever see something like this in code that you're finding on Google or something, that's what this guy's for. So 0, or this will be this dot left tree dot depth. So that'll be the depth of left. And we'll say right depth is equal to this dot right tree equal to null 0 this dot right tree dot depth. So now we have the depth of our left and right tree, and we're going to return math.abs left depth minus right depth greater than 1. So doesn't matter which of these two is greater. We're going to get either a positive or a negative number. We'll take the absolute value of it. Now we have a positive number. If that number is greater than 1, dude's out of balance, right? And we'll return that. So that's going to be out of balance there for binary tree. Binary search tree just returns whether his root is out of balance. So now we should be able to ask the question, is out of balance, and we should get whatever. We should get a true right now, correct? Because the right half should have a depth that's 2 larger than the left half. 4 on the left, 6 on the right. Here's our true. We take out the z's. Now it should be false. We add 1 z, it should also be false. 2 z's should also be false. 1 z hasn't changed the depth. So, well, let's just test it just since we're here. So 1z should not have changed the depth. It should still be false. So this is from the library?
The Nest.
The Nest. They use a good amount of caramel. I like it.
Yeah.
Yeah, let's sample Starbucks version. The real Starbucks version. Close.
Real Starbucks is better.
I don't know. I would say they taste the same.
Yeah.
What's this?
They should taste the same.
Well,
they use Starbucks.
They use Starbucks stuff there, but they don't have professionally trained Starbucks baristas down there. Just like a sandwich in the cafeteria doesn't taste the same as Subway because they don't have sandwich artists.
I don't know. I think Larry's pretty good at making sandwiches.
I really don't think that the Subway people go to the sandwich college like they have in the commercials. I don't believe that for a heartbeat. And I know the McDonald's people don't. My wife has posted pictures of filet of fish sandwiches from McDonald's where the cheese is on top of the bun. How hard is it to hit the fish with the cheese before you put the bun on? And these are the same folks that want...
$15.
Exactly. These are the same folks that want $15. I want McDonald's to upgrade to machines. I think they're somewhere in the Milwaukee area, they have one of the machines for ordering at McDonald's. Like you go up to the kiosk to order. McDonald's is proving that they could do this if they want to. I think they should. I mean, I'd rather order at a screen and not rely on the McDonald's person to get the order right. And then I want a robot making the sandwich because, I mean, I feel like there's a higher probability of the cheese making it inside the sandwich with a robot.
More sanitary, too.
Oh, I don't care. I mean, germs are flavor. I mean, you don't view the world that way, but if you had things too sanitary, we would all be sick all the time because we wouldn't have the opportunity to build up our immune system. That's why every single time you're at a barbecue, you should rub your hands in the dirt first and and then eat your burger.
They don't taste bad, too. It tastes dirty.
What do you mean? Have you watched Bear Grylls?
Yeah.
Some of the stuff he makes people eat?
He also like skins a deer and like will sleep inside of it for warmth.
I like the screw ups on some of those shows. I mean, obviously there's a camera crew there, right? It's not like he's sitting there with one of the selfie sticks while they're climbing a mountain. So I like when they're like presenting a place as being like completely out in the wilderness. Yeah, all of a sudden you see like a really busy interstate along the side. These guys this is like right outside of San Francisco. It's nowhere near the Tibetan wilderness like they're presenting here. Because they had an episode where President Obama was on the show. It was actually a pretty entertaining episode.
Out in the wilderness?
Yeah. Yeah, see, I'm of the opinion that, in general, presidents are much cooler people than people give them credit for.
Yeah.
So I think Obama comes off as a very personable person in those settings. I mean, forget about politics and stuff. I'm not political anyways, but he seems like a cool enough guy to me. And I like the fact that he plays basketball with some NBA people at the White House.
And he goes on ESPN all the time. Like, he does his bracket there.
Yeah, that's how it should be. I mean, that's what you should be doing instead of running the country.
Yeah.
Important stuff.
March Madness.
That's what gets you reelected. But yeah, so I mean, I'm sure that when Obama was on the show, I doubt very much they were in the middle of nowhere, and I doubt very much he was taking humongous risks in terms of climbing cliff sides and stuff. They made it look like it, but he was probably on 4 different, belay ropes, and they just photoshopped it out or something. I would be on 4 different belay ropes for a different reason.
It's funny if it comes out that he was like in a green Like,
Green screen. Didn't even leave the White House.
They were in the green room.
Seriously, same place they filmed the moon landing. That's a conspiracy theory, right?
That and 9/11, it was the inside job. You seen all that stuff?
Well, I mean, let's. Do you doubt that for a second that there's corruption in politics?
I don't doubt that. I don't think you'd kill however many people.
Well, some of these people are pretty corrupt. Just because it was an inside job doesn't mean it wasn't still terrorism. I mean, yeah, there's some pretty power-hungry people out there. You know, I think that's probably why Trump is so popular right now. I mean, logic does not play that out well, right? I mean, he seems like a lunatic, but the fact that the political scene doesn't own him because he's not taking any of their money, the very least probably means that he's not corrupt yet. Well, he's corrupt in different ways. So who knows?
Vermin Supreme?
Who?
Vermin Supreme?
Vermin Supreme?
Yes, you should look him up just for 1 second.
He's running for president.
Oh, is he really?
He's pretty great. He's run the last like 3 times.
He's run.
He's got some pretty
So,
great stats.
vermin like that?
No, at my end. This might be
Right there.
Okay. Oh, yeah.
Where's a boot on his head?
No, that's not. Oh, that's a boot. I was thinking that was a Grand Wizard type cap.
We're going to have ponies as our currency. It's going to be a law that you brush your teeth because tooth decay is ruining America. What else? There's a bunch of other random things. And basically at the end he goes, vote for Vermin Supreme is the vote you're throwing away. So he ends all his speeches.
Oh, I love this guy.
You should watch his video sometime. It's pretty good.
I've never. How come he doesn't make it on any of the televised debates?
Probably they're scared he might actually win.
That would actually be kind of funny. So the way it looks like it's going to be what, Hillary Clinton versus Trump versus Vermin Supreme.
Yeah.
That could be a much tighter race than it should be. Makes me. How many of you have seen the movie Idiocracy? It's a really good movie, and it makes fun of something, but while you're watching it, you kind of believe it could happen. Like a society is degrading. So the idea of Idiocracy is there's this guy, who is it? Oh, not Owen Wilson, Luke Wilson? Yeah. Owen's brother, right? So the guy who was in Old School, the Godfather from Old School, he's in it, and Maya Rudolph from Saturday Night Live. So these are two people, and he's like Joe Average in the military. So he gets volunteered to do this cryogenics program where they freeze them, and they're going to wake them up in the future, but then funding gets cut or something. They forget to take them out. Okay, so now it's like way in the future, and so him and Maya Rudolph come out. Now he's the smartest man alive. So Joe Average is now the smartest man alive because what they were kind of talking about what could happen is like they were looking at smart people, and they were saying, oh well, we could never bring a child into this world in the the current economic whatever. So basically the gene pool was going not in a good direction. You had the hillbillies out in the middle of nowhere. This lady, she was just in the kitchen. All of a sudden, she has another kid. It's like, see, I told you I was pregnant. And so basically, people become stupid, is what happens more than they are now. And so now you're in a society where everything is they're watering plants with Gatorade, except it's not called Gatorade. It's called Brondo. It's actually funny commercials dealing with Brondo. You can watch those on YouTube. But they don't understand why the plants aren't growing. So, this Joe Average is now the smartest man alive, says, well, maybe you should use water to, like, oh, you mean like from the toilet? But it's a funny movie. But the interesting thing is it's believable enough to not completely discount it, right? Like one of the guys got his law degree from Costco.
The one where the president was like a pro wrestler.
Yeah. Right.
Porn star.
He was a pro wrestler. Yeah.
He was like several different.
Oh, could be. Yeah, it could be. Yeah, I mean,
I've seen a parody of
yeah,
that.
the movie's pretty entertaining. It's worth watching. And the thing is that it should be like completely from left field, but when you're watching it, you're like, this could happen. It's not as far-fetched as it should be, is kind of the problem.
Like you should be paying attention to politics and how it's basically like a third grade school year right now.
Yeah, it's pretty sad. I mean, I'm not political. I've never voted for any election, president or anything like that. I give up my right to complain, but yeah, I just figure there's plenty of people who really care. I'll just stick with whatever we get and deal with the consequences. I think I mean, I guess I'm of the opinion that we're screwed either way, I guess. So, so whatever. I know there's a lot of people who really do care, so let them educate themselves and go and vote and all that stuff. But yeah, I'm looking forward to this election strictly from an entertainment perspective. I mean, it's in some ways somewhat scary. Like, I hope Trump wins for no other reason than entertainment value. He would make the funniest Saturday Night Live skits. I think certainly the way we do things would change. Not necessarily for the better. Possibly for the better, but not necessarily, but they would definitely shift. I mean, we get that Mexican wall, apparently, which seems to be, that's kind of Berlin Wall-esque.
Is it gonna be like 100 feet tall or something?
Who even knows? I don't know. The United States dome. Or should we just build the dome over Mexico? That way the diseases and stuff don't get out from those lesser.
If you want to see a funny debate, though, look up At Midnight Presidential Debate. Have you ever seen the show At Midnight?
Possibly.
It's on Comedy Central, but usually they do stupid stuff. But basically, this time they made it like a presidential debate.
Okay, like a legit thing.
Well,
They try to make it look more legit.
Yeah, and it was between Trump and Bernie, and just the two.
But the real people or
fake people
okay, I got it.
dressed up like them and did like great accents, and it was really funny.
I got you. Yeah, that's. Well, the funny, what was it? George W. Bush there was a professional guy that did an impersonation of George W. Bush, and he had him at one of the press dinners where it had George Bush at one podium and then the impersonator at the other. And George Bush would say the presidential thing, and the impersonator would say like what he would translate.
Yeah.
He's like, I'm absolutely delighted to be here tonight. And the other guy was like, here I am. It's pretty funny. You should look up George W. Bush impersonator press dinner or something sometime. I kind of like presidents with a good sense of humor like that. It's just like an IT. So let's connect it to our major, right? It's really just like an IT professional. Who would want to be a president? It's a thankless job, right? When everything's going well, nobody says anything. When stuff hits the fan, you're incompetent. Look at it from a student's perspective. So we take Mark Newhouse down in IT. Good guy, competent guy, works really hard, cares about our network. But hey, if you can't play your Xbox Live, who are the monkeys we're hiring down there? Seriously, that's an interesting way to view our field. So really, who wants to be an IT professional then, right? That's why we should just all be pastors. What's the worst that happens? You just say you had an off day? Had some bad, vegetable lasagna last night. That's why the sermon was a little off.
What does that have to do with eating vegetables?
I don't know. Vegetables and lasagna doesn't make any sense. You shouldn't be eating that.
Make, instead of noodles, they use eggplant or whatever now. Have you seen those?
I have.
Why? Why make those? Noodles taste so much better than vegetables.
Well, but some people don't want to. They're like vegan no. You should be okay with pasta for vegan.
Well, if you have
Oh yeah. But also gluten intolerance. Yeah, gluten intolerance is a big thing now, right? That's why we have the whole line in the cafeteria for the allergen-free stuff. And half the gluten stuff we've done to ourselves, right? If you read some of the books on gluten is a naturally occurring protein, but the wheat we eat today isn't the wheat that existed 100 years ago, because we've genetically modified it to feed more people. So we essentially just created new allergens or new ways for us to get sick from our own stuff. Yeah, we'll end up killing ourselves, so it'll just work out all right. Hopefully it's before the Idiocracy stuff becomes true. All right, so now we know we're out of balance. The master of transitions. Okay. All right, so right now we're not out of balance because we've removed one z. So now we should be one depth difference now. So we should still be in balance, right? So even though the right side is one depth larger than the left, it's not a problem right now. Okay, out of balance is still false, but we add that one additional z. Now it's a depth difference of 2. All right, so now we need to be able to detect how we're out of balance. I think we've already seen this true, but let's just see it again for the sake of whatever. Okay, so go back here. Let's go back to our AVL trees. All right, so again, here's an example of out of balance. So 2, we have a depth of 2 on the left and a depth of 0 on the right. 2 on the right, 0 on the left. 2, 0, but depending on how it's out of balance. Okay, so now we need to decide which of these cases. We need to identify how we are out of balance. Okay, now how do we go about doing that? Part of it's going to be, let's look at the 2 different ways of doing it. Right now we're out of balance. We've added enough z's where we're out of balance. We can check the entire tree and try to find out how we're out of balance, right? But that might be pretty tedious because now you need to kind of verbosely go through the entire tree and try to almost reverse engineer how that tree was built. But if we check for out of balance after each add, at that point in time, if we become out of balance, we know it's related to the very last thing we added, right? That way we can determine why we're out of balance. Okay, so it's very important that we actually check for balance problems after an add. So we know exactly which part of the tree to focus on. Okay, so let's go ahead and let's check this. Let's move our out of balance for right now. Inside our tree. So we'll add something and then we'll check for out of balance. So we should get several of these printed out. And let's see if we become out of balance somewhere in the middle. We might. All right, so not out of balance, not out of balance. Now we are out of balance. We would still be out of balance because we didn't fix it, right? So we do actually become out of balance early on. So the third add, so FBA is where we actually become out of balance. So let's actually go in here and build our tree related to that because we're going to need to see that in order to work on our fixes. All right, so there's our F. So we add the F. Next, we're going to add the B. So B is less than F. So that's going to go here. Then we're going to add the A. That's less. Okay, so we're out of balance here, right? Now, we added the F, we asked, are we out of the balance? We were not. We added the B, we asked if we're out of the balance. We're not. Now we just added the A. We asked, are we out of the balance? We are. So now we need to follow up and say, how are we out of balance? Well, we know the element we just added is the A. All right, so we can look at the root node and ask, is this to the left or to the right? Well, we know this is to the left, so we know our out of balance issue is on the left-hand side, correct? All right, so let's go in. So we're going to do just text first and have it tell us how we're out of balance. So we're going to say public string. Actually, let's just do public void. How are we out of balance? It's a wimpier sneeze than I would have expected.
I have a friend that when she sneezes, I feel like I can't breathe because they're weaker than that.
Really?
It's like that.
Because you're like a soccer superstar, right?
Yeah.
Because I would think there would be like crazy lung capacity and stuff like that. So,
I'm out of shape right now.
oh, that's it? No.
To do a study.
You see, I don't know what that feels like to be out of shape. Why does everybody just start laughing? That's not fair. That's not nice. I mean, I think what I'm really saying is I'm always in shape. I do distance sprinting. Actually, I can tell when I'm out of shape. So during the summer, I do a lot of walking with golf and stuff. But during the winter, I know I'm out of shape when I go from the bedroom to the couch, and I'm not winded, but I'm closer to winded than I should be.
Go up or down the stairs?
No, this is literally about a 30-foot walk. Yeah, ish. Maybe it's more.
You have your hoverboard, so that shouldn't be a problem.
Well, I don't park it. My wife doesn't let me park it in the bedroom because of the fire risk. That would be awesome. But I'd have to train myself to get on the hoverboard without actually standing up from the bed. Like you stand up onto the hoverboard, as opposed to stand up first and then step on it, because I don't know, that's exercise. But actually now I can take the hoverboard to more places in the house because we can keep our doors open because we don't have the cats anymore. I can zip all over the place now. There's perks. All right, so how are we out of balance? We're going to ask our binary search tree this. So this is going to be a follow-up to when we actually determine we're out of balance. So let's go ahead and actually add that into our main activity. So we'll turn this into an if statement. So if we are out of balance, then tree.how are we out of balance? With the expectation it's going to print that out. So our very first one, it should be left, right? That's the way we're currently out of balance, is left. So our tree looks like this. All right. So let's go back in here. So how are we out of balance? Well, we know the last guy we just added was us know that the last thing we just added in our current example was that A. So we need to probably pass in here the value that was added, so we can make some determination on where the problem is. So let's start with that. Are we doing it as strings or are we doing it as chars? Yep, we're doing it as chars. All right, so we'll take in a char val as the parameter here, and we're going to ask the question, where should val go relative to the root node? Okay, so this is our goal of determining which side. So we're going to say, where are we out of balance? Initially, left or right? All right, so we're going to need to ask our root node. So we know we wouldn't be out of balance unless we actually had a tree, right? So we don't really need to ask that if things are equal to null stuff. So we're going to say if this dot root dot get payload, so that's the payload, if val is less than or equal to that, we're going to say string out of balance initial. Let's set this equal to right by default, because we're testing for left. All right, so if out of balance initial is, well, if val is less than our current root, that means that we actually added it to the left, so we'll update out of balance initial to left, otherwise it'll stay right. All right, and then we need to say, where are we out of balance secondarily? Left or right? String out of balance secondarily, whatever. And we'll start this off as right again. So in order to determine that, we have to follow the value down, right? So we need to figure out where that last guy lived, or where he ultimately found a home. Okay, so go ahead.
Question about that last if statement.
This guy?
You say, yeah, value is less than the start root. Why is it less than? Why isn't it greater than? Because if you're looking at the root, wouldn't it have to be, if it's less than, wouldn't it go to the right?
If it's less than or equal to, it goes to the left. So for instance, B, because it's less than or equal to F, we add it to the left of it. A is less than or equal to F, it's less than or equal to B, so it goes to the left of it.
Mm-hmm.
So what we're doing is we're starting off assuming that it's out of balance to the right, and then we update it to the left if we do find it to be out of balance. So we come back here, we're asking, in this case, val, so let's use, our val in this case is A, right? That's the guy we just added that's knocked this out of balance. So we're saying if A is less than F, or less than or equal to, okay, if A is less than or equal to F, that means that, since this was the last guy we added, that means that,
I'm confused because it's letters. Now that I think of it as numbers, that makes sense.
Yep. So, since this guy is less than F in terms of the alphabet,
Okay.
he's actually was added to the left, and therefore, if we're currently out of balance, we're out of balance left. Okay? All right, so now we're here, and now we need to figure out, now that we know we're interested in the left-hand side, this guy, we need to know where that last node was actually added. Okay, now here's an interesting issue. We know that A was just added. What if we had two A's? Okay, or let's actually go the opposite route. Let's do C. Something like this. So if C was the value we just added, the actual out of balance is left-right, correct? So we need to find out where that value that we just added actually ended up living. All right? Now, at what point can we make the determination that it is the right or the left? Don't we need to go down all the way to the bottom of the tree? But how far down the tree do we go? Anything that knocks something out of business is going to be, out of balance, is going to be a leaf node. One of these bottom guys, right? But how deep down the tree do we need to go before we hit the bottom? In this case, our tree is pretty shallow. It just happens to be in an early state out of balance, just because of the nature of adding stuff to an empty tree. So how do I determine whether that value was left or right? We need to follow it down the tree. So our current example, let's just throw the C over to the side right now. We're trying to determine where this A on the left-hand side, because we've already determined that we're out of balance to the left, where this A ultimately got us out of balance. So we need to find this A in the tree. So we know we're going to look left here, and we're looking for an A. So when we come down here, we hit the B. Should A come, well, first of all, is this the value we were looking for? No, we still need to ask, right? Even though we've only gone down one level, so we couldn't be out of balance yet, but in terms of an algorithm, we're still going to have to ask. Is this the value we're looking for? No. Should the value we're looking for come to the left or to the right of this? It should come to the left of this. Now, at this point in time, generically speaking, can we 100% guarantee that the problem is a left? Not necessarily. Because if we're looking for, let's see, let's change this to a C, change this to a B. So we would come like that, correct? To find out where we're out of balance. So we need to keep following the rabbit hole down until we actually get to the point where we find the value we're looking for. And we need to keep track of which turns we took each time along the way. So A comes to the left of this. Well, is this the value we're looking for? No. Is this the value we're looking for? No. Is this the value we're looking for? Yes. What was the last turn we took? The last thing we did is we went left. Okay, so we went left, that's last turn. Then we went left again, that's last turn. We're now landed where we're supposed to be. Last turn is equal to left, so we must be out of balance. Initial concatenated with last. So this is left in this case. But could we create a scenario where where it's out of balance? Here, I need to do. I'm going to throw a G on here real quick just to add a layer of balance on the right-hand side so I can go one level deeper. And then we're going to make this a C. And then we're going to make this a B. Let's see. Actually, I want to make this an A. This is how I want us to be out of balance. All right, so we were in balance before we added that second A. Then we added the second A, and now we're out of balance. Correct? All right, so is this the value we're looking for? No. We go left. Is this the value we're looking for? No. We go left. So last move is left. Is this the value we're looking for? Yes, but it's not. It looks like the value we're looking for, but the actual A that threw us out of balance was this guy. That make sense? So we have the char A that matches here, but that's not related to the tree we just added. It's not actually this guy. Right, so we need to somehow be able to get down to this value when we're adding him to know the last place he was added. So how do I identify this node versus this node when I am determining how this tree is out of balance? Because I need to know how it's out of balance before I can fix the balance problem. Good.
You just have to go until there's like a node, next node sort of deal, where you make sure that it is a leaf, because
Okay.
if it does set it off, it's gotta be a leaf.
Okay. So even though this guy looks like the right answer, given that he has a left child, like we would ask the question, does this look like the answer? Yes. Now, if I were to add, it's always going to be to the left. If I was going to add myself to this and it's equal to it, I always need to check the left child. I don't even need to ask the question. It would be the left child where this guy would live, because we've decided that less than or equal to goes left. If this guy has a left child, we're not done. So we drop down to this level. That gets us to where we are. Fine, they were both left moves, but this actually tells us the left move that we were looking for. That makes sense? So you're right, we need to make sure we're a leaf node. So we've got to be careful about a false positive. Let's come back into here. So are we out of order? This is our first thing. So out of balance secondarily, we now need to ask, we're in our binary search tree here. So we cannot just do it at the superficial level at the top. We now need to go into our binary tree and say, what was the last direction to add a certain value? So we're going to say, let's see. We actually aren't even going to default it. We're going to say, this guy is going to be equal to this dot root dot out of balance secondarily, whatever. Let's just say close enough. So now we need to go write this function inside of binary tree. Public string out of balance secondarily. It's going to look like this. And this guy needs to now go and traverse through this tree looking for a char. All right, so we're going to need to pass it a char in here, and the char we're passing it is going to be val. So that's the guy we're looking for being out of balance. All right, so binary tree is going to go through and it's going to walk through our tree until it can actually determine val is out of balance. Well, we know we wouldn't be calling this unless we were out of balance. So we need to walk through this until we can determine the last road taken, right? All right, so we know that we already have a payload. So we're going to ask the question, if this dot payload is equal to val and this dot left tree is equal to null. This is, are we looking at a matching payload, and are we, as you pointed out, a leaf node? Are both of those things true? All right, so if both of those things are true, then what are we going to do? We need to keep track of the last move we made. Okay, the last move we made. So how do I know right here the last move we made? We don't know whether this was the first call to the binary trees out of balance secondarily, or if this was another one. So if we're not at the end, then what are we going to do here? If we're not at the end, then we need to call our out of balance secondarily on our left child. Well, actually, we need to decide which side it should go on to. So if we don't match, or we're not a leaf node, we need to keep traversing the tree. And ultimately return left or right. Here, well, we can just do it. We need to return the last turn we made. So now I'll ask the question here for your homework. How do we know what was the last turn? All right, so for your homework assignment, finish writing out of balance secondarily, which should allow you to finish writing how are we out of balance, ultimately printing out. So we're going to say, finally, print out how we are out of balance. So that's your homework assignment, is ultimately print out how we're out of balance. You don't have to rebalance anything, just print out how we're out of balance. Make sense? All right, I'll push this up to GitHub. I'll put the assignment up, and I will see everybody on Thursday.
I have a question. So I know I talked to you about it, I think last semester,